All right. Hello, class. Good afternoon. I hope you had a good weekend. Uh, Hello, Sebastian. Um, so let's see. What did I do this weekend? I'm like this close to having all of the items for my forge set up. So I got a couple items yesterday. I got my tongs, um, so I can take really hot pieces of metal out of my forge. Um, I got my 3 pound sledgehammer so I can whack some steel. Um, and once I've shaped it into a knife, I got my whetstone so that I can sharpen it. So I'm pretty psyched. Probably end of this week, I'll be attempting to forge my first knife. So something I've been wanting to try out for a long time. So, and then just a couple minutes ago, I had ordered this textbook. Um, when I was in um, when I was in high school, I took AP chemistry, and I got a good enough grade on the AP exam where I haven't had to take any chemistry since high school, and consequently, all of my chemistry knowledge is what I've learned through physics. But I've been thinking about it, and I'm like, well, I should um, probably bone up on my chemistry. So I got this textbook from abooks.com used, and it costs $6 with free shipping. That's a pretty good deal, if you ask me. It's used, but if you buy it new off Amazon, it's like $120. So big savings. And it's written by a professor Oxtoby, who is a professor at Pomona College. So I don't know. Does Does anyone know someone with the last name Oxtoby in the Claremont community? Might be. Uh, okay, so a couple of announcements. Your AP exam is next Thursday. On Wednesday, we're going to have just a question and answer session. So next week, Wednesday, um, it'll just be, you guys asking questions. Um, and then we're going to take Thursday and Friday off because you guys are taking the AP exam. And yeah, so we'll get started back up again on Monday. And this afternoon, I'll be posting a straw poll to ask you guys what you want to learn after the AP exam. Okay, so that'll help me plan. So that's what we're going to do. All right. Um, so I will be doing 4 pages from the workbook today, and we're back with energy. So here's our workbook question. And let me say hello to everyone else who made a comment. Hello, Zena. Hello, Elena. Hello, Vicky. Hello, Ethan. Thank you for watching. All right, so what does it say? A toy car is released from rest on a smooth track with a loop-de-loop. The car is released with a height h such that it never loses contact with the track. The system includes the car and the earth. So what that means is that because the system includes the earth, it means we include gravitational potential energy in our energy for the system. Rotational effects from the wheels, friction, and air resistance can be ignored. Okay, part A. Draw and label free body diagrams on the figure shown above that depicts the forces exerted on the car as it goes down the ramp and at the top of the loop. Draw the relative lengths of all vectors to reflect the relative magnitudes of the forces. Each force must be represented with a distinct arrow starting on and pointing away from the car. So, um, we're going to have a normal force, which points perpendicular to the loop. So that's one force. And then we're going to have a weight force that points straight downward. Okay? And so those are the two forces. Because we don't have friction or air resistance. Then we're also going to have the same thing here. Normal force points away from the surface, which would be downward in this case. And then weight force also points downward. So we have two downward forces. I'm not labeling these. You would want to label them on the actual exam. Part B, fill in the energy bar chart below with the initial energy and the final energy. Okay, so initially we have all gravitational potential energy. Okay, so we have gravitational potential energy that goes up to here. All right, we have no kinetic energy. So U sub S, which stands for system energy, is going to be there. Now, when we go to the final energy, we're still going to have the same amount of system energy. Oh, wait a second. I think U stands for system gravitational potential energy. I don't know. You know what? I'm just not going to worry about what U sub S means, because they don't even say what these things mean. It's stupid. The final energy, our gravitational potential energy, we're at about a height that's a little bit more than 50%. So we're going to have a little bit more than 50% gravitational potential. Okay? Now, if you look at it, I drew this so that my initial gravitational potential energy is 1, 2, 3, 4, 5, 6, 7, 8, 9 bars. And my final gravitational potential energy is 1, 2, 3, 4, 5, 6, 7. So that means that I would have 2 bars for kinetic energy. Does that make sense? We want the total height of all the bars needs to be constant, right? Because that would mean that energy is conserved. So if I take this bar and I stack it, if I take this bar and I stack it on top of the other bar, it has to have the same height as I did originally. Okay? All right, citing the bar chart, explain why the release height must be greater than the diameter of the loop. Okay, so I would say we must have h greater than 2r so that there is enough gravitational potential energy to reach the top of the loop. If I should say to reach the top of the loop with a non-zero speed. We can go ahead and work out the equation. We can say if the initial energy equals the final energy, then we start out with mgh, and we end up with mg times 2r, because that's the diameter, and then we also end up with kinetic energy. Okay? So we can see that 1/2 mv squared equals mg times the quantity h minus 2r. So we have to have h greater than 2r in order to make this greater than 0. Kinetic energy can't be negative, right? So we can't have negative kinetic energy at the top of the loop. So I would say something along those lines. All right. Data analysis. Carlos determines that the normal force the car experiences at the top of the loop can be determined by using the equation F sub n equals mg over h. To test the equation, he releases the cart from various heights and records the normal force at the top of the loop from a sensor in the track. The graph below is the student's plot of the data for F sub n as a function of height. All right. Are these consistent with Carlos's equation? Then I would say absolutely not. Absolutely not. The equation, or the expression, I should say, 2mg over h decreases as h increases. The graph does the opposite. The graph, you can see it increases as the height increases. So there's no way this is consistent. Blake suggests that regardless of whether or not the data above are consistent with the equation could be incorrect for other reasons. Does the equation make physical sense? Okay, let's look at the equation. Well, as the weight of the car goes up, the normal force should go up, right? Because you're trying to move around a heavier cart. So I would say that aspect of it makes sense. For me, here's what I would say. I would say so notice how the first question is saying, assuming this equation is correct, is this data matching the equation? Okay, which it doesn't match the equation. Okay, now it's saying, could the equation be wrong? All right, so I have a couple of statements here. I would say the equation makes no sense. Why? The units are not even units of force. Why do I say that? Well, mg is force. Mg is the weight force, right? So we're saying a force equals a force divided by height. So the left-hand side of the equation has units of force. The right-hand side does not have units of force. So how could you set two things that don't have the same units equal to each other? It's like you're saying apples and oranges are equal, okay? So that's one thing that is wrong. Also, if h increases, the car has more speed at the top of the loop. I think that's obvious due to energy considerations, right? More speed at the top of the loop means a greater centripetal force is required to move the car in a circle. Thus, the normal force should increase. So, I hope that makes sense. All right. What would happen if Carlos released the car from a height of 0.8 meters? The car completes the loop or the car does not complete the loop. Justify your claim using relevant features of the data shown. So if we start out at a height of 0, so let's extend this line. Okay, I'm going to extend the line back. Looks like maybe right there. So we can see that the normal force becomes 0 when the height is about 1 meter. Okay, so if the height is, and remember, the normal force becoming 0 means that there's a loss of contact. Okay, so the normal force cannot be negative. It can point downward, but once it goes to 0, it's not like this line just continues. Okay, it can't continue. It's just once it reaches 0, the line doesn't exist anymore because there's no more contact. Okay, so if we look at 0.8 meters is like right here. So we can see that we would need to have a negative normal force. So we've lost contact with the loop at 0.8 meters. Okay, so I would say that the car does not complete the loop. So I would say as h decreases, we can see that the normal force equals 0 when h equals 1 meter. All right. The car, so that means that the car will lose contact with the loop if h is less than 1 meter. 0.8 meters is less than 1 meter. All right, cool. So moving on. An ideal spring of unstretched length L0 equals 0.25 meters and spring constant K equals 50 newtons per meter is hung vertically above a level floor as shown in the figure. A 1 kilogram block is attached to the spring when it is at its natural length, released and then allowed to move freely. Draw and label the forces exerted on the block in the diagram. Qualitatively consider the relative magnitudes of the forces. Okay, so here we have weight force, but we have no elastic force. Okay. Why do we have no elastic force? It's because the spring is at its natural length. Once the mass starts to fall, then the mass gets, or the spring gets stretched, and so we're going to have an upward elastic force. Now, I don't know, it kind of depends. Is this dashed line supposed to represent, oh, it's a dotted line. This dotted line is the equilibrium point of the block spring system, so that means that the mass would just sit there, and so these two forces have to have equal size at equilibrium. Okay? Part B, calculate how much the spring has stretched when the block is at equilibrium. So when the block is at equilibrium, we're going to have, so we're using net force equals ma. And if it's at equilibrium, then the net force is 0 because it has no acceleration there. It can just sit there. What are the forces? We have an elastic force, which is kx going up, and we have a weight force, which is going down. So that means that x equals mg over k, doing algebra. So we have a mass of 1, gravity is 10, and k is 50. So that means it is 0.2 meters, is how much it stretches. That's how much it stretches beyond its natural length. Calculate the height of the equilibrium position of the spring with respect to the floor. So what we're saying is this distance is 0.25 meters, and then the equilibrium is 0.2 meters below that, okay? So that means that this total distance is 0.45 meters. Okay? That's 0.45 meters. This whole distance is 1 meter. So that means that the remainder that's left over is 0.55 meters. So that's a little bit tricky because they didn't, so I would say it's 1 minus 0.45 equals 0.55 meters. All right, so it's, yeah, it's, there you have it. Angela is tasked with completing an energy bar charts for the scenario described above and creates the chart. Oh, you know what? Maybe S means elastic potential energy, like potential energy of the spring. They finally, I really wish they would say what each of those symbols is. Angela is tasked with completing energy bar charts for the scenario described above and creates the chart for the time just as the block is released. Complete the energy bar chart below and right that would depict the energy of the blocker spring system as the block passes through equilibrium. So we start out with 7.5 joules. How much gravitational potential energy do we have at equilibrium? Well, the height of the equilibrium position is 0.55 meters, right? So that means that when passing through equilibrium, we have mgy, which would be 1 times 10 times, and we said it's a height of 0.55. So that equals 5.5 joules. Okay? So we have 5.5 joules there. So let me draw 5.5 joules. That's the gravitational potential energy. As far as elastic potential energy, that's 1/2 kx squared. So how much is the well, we have 0.5 times the stiffness, which it said was 50 up here, I believe. Stiffness is 50. And then what is the extension? The extension is 0.2. Notice that the total length of the spring is 0.45, but when we're calculating elastic potential energy, we calculate how much is it stretched beyond its natural length. So 0.2 squared. So we have 0.5 times 50 times 0.2 squared. That gives 1 joule. So that means that our elastic potential energy is simply that. And then the kinetic energy is going to be the total energy minus the gravitational potential energy minus the elastic potential energy. So the total energy is 7.5 joules from right there. Okay? So we have 7.5 minus the gravitational potential, which is 5.5 minus 1. That gives us 1 joule of kinetic energy. Boom. So that's what it will look like. Dominique says that the height above the ground doesn't matter, only the change in height is relevant. She considers the equilibrium position to be zero gravitational potential energy. Complete the bar charts. Okay, so if we consider the equilibrium position to be zero gravitational potential energy, then we start out with a height of 0.2 meters, not 0.55. So our initial gravitational potential energy is going to be mgy. It's going to be 1 times 10 times 0.2, which is 2 joules. Okay? When we are passing through equilibrium, we have a height of 0. So now we have no gravitational potential energy. The elastic potential energy, the spring is still stretched the same amount, so we would have 1 joule of elastic potential energy passing through equilibrium. By the way, these are both 0. And then the kinetic energy would be the remainder of the initial energy, which would be 1 joule, right? Because it would be 2, these two add up to 2 joules. Use these results, the results of your bar charts, to show that Dominique's claim that the 0 point of gravitational potential energy does not affect the behavior of the block spring Earth system. All right. We can see, I would say we can see, that when passing through equilibrium, the kinetic energy of the mass and the elastic potential energy of the spring are the same as they were when the 0 of gravitational potential energy was at a different location. Thus, the 0 of GPE has no effect on the speed of the block or the extension of the spring. So it doesn't matter, okay? And I taught you guys that when we did energy. All right, so that's 109. So that means that that I did all the questions that I wanted to do. So I think I'm done. So I hope you guys have a wonderful um, rest of your afternoon. And I'll be in touch on Discord about how with a straw poll for you guys to vote on what you want to learn next after the AP exam. Okay? I will talk to you next time. Bye now.